Good day, everyone. We are busy with moment of inertia for mathematics today. So we'll go through this question. It says sketch the graph of y equal to 2x minus x squared. I'm underlining the important aspect and show the script that we will use to calculate the volume generated when the area bounded by the curve x equal to 0 and y equal to 1 is rotated about the y-axis. So after that, we'll calculate the volume described in A, then we'll calculate the moment of inertia and express our answer in terms of the mass. So let's go to the first part. You see I've identified what is important to me, y equal to 2x minus x squared. The next important thing is the line x equal to 0. Another name for x equal to 0 is the y-axis, and then the line y equal to 1. So it means when I'm done sketching my graphs, for the purposes of areas and volume, I always prefer to call the x and y-axis graphs, because when I'm done sketching these three graphs, then I must remember that the portion I'm shading must be surrounded by three graphs. So that is it. Then the last thing that is important to me is my y-axis rotation, because that immediately tells me how my formula for volume must begin. So how it ends, I'll be told by the script in my diagram. So these two graphs are easy to sketch. So the one that I will need to do a little bit of a job there is this one, which is obviously a parabola, but because my A is negative, it means I have already seen the shape. It's called the surface by some students, so that is my shape. But before I sketch it, I need to be so sure where does it pass, because they didn't tell me anything about calculation point of intersection. So for the graph y equal to 2x minus x squared, I need to say if x is equal to 0, what will be my y? You see that if you replace x by 0, y will also be 0. So this means this graph must pass through the origin, and I cannot settle for one point to sketch that graph. I've seen that it passes through the origin. What if y is equal to 0? This means I will equate 2x minus x squared to 0. Then it's a quadratic, so with two terms, I must not use the formula. So I can factorize to get 2 minus x is equal to 0, which takes me again to the point x equal to 0, which we already saw it there. And the other one is x equal to 2 if you equate that to 0. So my points are 0, 0, and 2 for x, and 0 for y. So now I've got 2 points, but 2 points are just not enough for a parabola. If you want to be very sure of the exact point where a parabola passes, you need the turning point. So for the turning point of a parabola, the equation of the line of symmetry should help us. I think it's x equal to negative b on 2a. So for this parabola, my b is a 2, is the coefficient of x, so I get negative 2 on 2a. My a is negative 1, the coefficient of x squared, so that gives me a 1. So if I now substitute this into the equation of the parabola, I should be able to get my y. So if I substitute x as 1, I will get 2 into 1 minus 1 squared. That is 2 minus 1, which is 1. So that tells me that my turning points are 1, 1. So you see, technically, the y coordinate corresponds to the other graph. So I can now sketch my three graphs. So if I'm sketching my three graphs, all the points I've identified so far, there's none that is negative. So that gives me advice that I should stay in the first quadrant. So in my first quadrant, I need y equal to 1, which is a graph that touches the y-axis at 1. So this can be my 1. I will say this is my y equal to 1. X equal to 0 corresponds to the y-axis. Then I need the point 0, 0. I need the point 1, 1. If I say this is my 1 on the x, then that will be 2 because I also need the point 2, 0. So these are the points that my graph must pass through. The parabola will touch the x-axis there, then it will turn at 1, 1, and it is a surface. So I'm expecting something of this nature. So this is my parabola that I've sketched. I've succeeded to sketch all the 3 graphs, the y-axis, y equal to 1, and the parabola. Then the portion I'm shading, you see why in the beginning I had to identify my 3 graphs, which I underlined. Because when it comes to shading, we must know that the y-axis we should treat it as a graph, and the portion we're shading must be surrounded by the 3 graphs. So there are considered that might make a mistake to shade here, and here you only have 2 graphs, which is 1 and 2. So that is not okay. So I must be shading the portion surrounded by the 3 graphs. You can see your y equal to 1, your parabola, and the y-axis, which is x equal to 0. So that is how I know the correct portion to shade. So from here, I can then put a strip in the shaded portion. So somebody can say a horizontal strip is okay because it keeps on touching the same 2 graphs, but considering the fact that when you put a strip, if I put a horizontal strip, I have to make x the subject. The 2 graphs that the strip is touching, I must make x the subject. So to make x the subject from the parabola becomes a problem because the square will be telling you that you need to factorize, and that doesn't really help. So here the best strip you can go for is a vertical strip, because if I use a vertical strip, I can keep on touching the same 2 graphs all the time. So in this particular situation, a vertical strip is the best. Because if I want to go for horizontal, I will find it difficult to make x the subject from the equation of the parabola. So if I make a vertical strip, you see it's touching 2 graphs. The graph above the strip is your first graph, we call it y1. The graph that passes below the strip is my second graph, which is y2. And that is the equation of the parabola. So I've got 2x minus x squared. So my strip extended out of the shaded portion will touch the x-axis and put in dx there, reminding me that if I'm calculating the volume, my formula must start with v1 since the rotation is y-axis rotation and ends with dx. So I think for the first part of the problem we are done. We can now go to the volume. Okay, so we are done with the A part. So the B part requires us to calculate the volume. So if I'm calculating the volume, I have to start by checking my rotation. It's y-axis rotation. So that tells me that my volume must start with Vy. Then how does it end? I look at my strip. If my strip touches the x-axis, then my volume must end with dx. So as an N6 student, if you go to page 5 of the formula sheet, you will see that formula. So I'm just going to complete it. I'll look for a formula that starts with Vy and ends with dx. So that formula has 2 pi outside, the integral from a to b. In here, you will just be seeing xy, then dx. But I have to try to accommodate the information in my graph. So if my graph has a vertical strip, then there is a graph touching the strip above it, which is called y1. Then the graph passing below the strip is called y2. So I will use y1 minus y2 to replace my y in my graph. If in my formula, if I was having a horizontal strip, I will be using x1 on the right minus x2 on the left to replace my x. So since we're only having a vertical strip in our diagram, it means we'll adjust this formula to get y1 minus y2. So that becomes our formula for the volume. And this formula is the shear method. How do we know that it's the shear method? You see that your strip is parallel to the axis of rotation. The axis of rotation is the y-axis. They are parallel. Or another way to see it is that there is 2 pi outside. So we can now start our calculations. So our A and B, we must be reading it from the x-axis since the formula says so. You know your strip chooses your formula for you and tells you where you read your limit. So I'll go to my x-axis and check where did I start shading. You see I started from 0, I ended at 1. So that's my A and B. Then my y1, I see it there, my y1 is 1. 2, which is my parabola. But because I'm having a negative and the parabola is made up of 2 terms, don't forget to open another bracket in there. Each time you write a negative and more than 1 term comes, it's important to put it in the bracket like that, so that I will then go on and open up my bracket. If I open up my bracket, I will get x into 1 minus 2x. These 2 negatives now become plus x squared dx. So I've opened up the inner bracket to allow the negative to go through. Then after, I will then open up the next bracket to allow x to go through. If x goes through, then I'll get x minus 2x squared plus x cubed dx. So I can now do my integration. So I will get 2 pi into a half of x squared once I integrate x minus 2/3 of x cubed, then plus 1/4 x to the power 4 from 0 to 1. Then I can now substitute my limit, starting with the upper limit. Since the upper limit is a 1, it makes life easy. If you substitute 1 everywhere, you get a 1, so I get 1/2 minus 2/3 plus 1/4. Then my lower limit will simply be a 0 minus a 0 plus a 0. Since I have to put 0 everywhere, there's x. So that means I will not bother myself with the lower limit. I will simply just calculate the upper limit. So if I take a half plus 1/4, that gives me 3/4. Then I subtract 2/3 from it, and subtracting 2 from 3, that gives me 1/12. Then I multiply by 2 pi, that will give me pi over 6. So my volume here is pi over 6 unit cube. So that's how simple it is to get our volume. So from our volume, we can now go to the C part. And with this volume, I'm confident because it's a positive answer. You only have to start getting worried if your volume is a negative answer. So the C part says we calculate moment of inertia. So when it comes to moment of inertia, all you need is just to go to your formula sheet. The advice I will give my students for N6 is to go to your formula sheet, either page 5 or page 6. You look for the general formula for moment of inertia. So the general formula, once I'm copying it, I just attach the axis of rotation to it. That general formula will be the integral of r squared dm from a to b, which is further equal to density, the integral from a to b of r squared dv. So that is the general formula for moment of inertia. So from this general formula, we have to develop it with the help of our diagram and our formula. So most especially if you were using the shell method as an N6 student, you must develop this formula. So as I was saying, each time you are calculating moment of inertia, my advice is go to your formula sheet, either the last formula on page 5 or the first on page 6. You copy down that general formula for moment of inertia. Most especially if your formula for volume was the shell method, you must develop this formula. If you were using the disk method, you don't really need this too much because your formula is under circular laminar on page 6. But you can see that we are dealing with the shell method because there's 2 pi outside. So to develop this general formula, I need to replace dV by my formula for the volume. So I'm going to do that. I'm copying my formula for the volume. It has 2 pi outside. This 2 pi will be accompanied by density, which is outside the general formula. So I must also attach the density. Then I get my integral from a to b. Then I'm leaving some little space for my r squared. Then I complete my formula for the volume, which starts with an x. Then in bracket y1 minus y2 dx. So I've tried to incorporate the 2 formulas by bringing the formula for the volume to take the position of dv. Now to do r, this axis of rotation is very important and my diagram. So I must go back to my diagram. I start from the center of my strip. I move in a straight line to the y-axis. So I will go back to my diagram. My diagram has a vertical strip. I will start from the center of that strip. I will move in a straight line to the y-axis. So it's important to indicate your movement. So this is my movement. So that is my movement. If my movement is horizontal, any horizontal distance, we describe it using x, since it is parallel to the x-axis. So that distance from the center of your strip to the y-axis, you can see very well it is a horizontal movement. So because of that, I will describe it using x. So that therefore means my r is a simple x, and that means r squared is an x squared. So that's how easy it is to define your r. So from here, I can now move on and start substituting my limit. A to b is the same 0 to 1. We got there, and now we'll be having x cubed here. Since r is x, r squared is x squared, then this other x is coming from the formula for your volume. So that creates an x cubed. Then your y1 is the same y1 you use from your diagram minus y2, which if you remember very well, we did that subtraction here. So a smart person will not be copying from the diagram again. You just remember that we did that subtraction in your volume. We created 1 minus 2x plus x squared. So I'll just copy from here. I get 1 minus 2x plus x squared there dx. Then I can open my bracket. So if I open my bracket, I get my 2 pi density. The integral from 0 to 1, that will be leading me to x cubed. If x cubed multiplies 1 minus 2x to the power 4, then plus x to the power 5 dx. So if I continue there with my integration, so my integration, I'll get my 2 pi density. If I integrate, I'll get 1 over 4, x to the power 4, minus 2 over 5, x to the power 5. Then you integrate x to the power 5, you get 1 over 6, x to the power 6, from 0 to 1. So I'm done with my integration. I guess I can continue this side to substitute my limit. So 2 pi density stays out. If I substitute the upper limit, which is 1, I'll place every x there by 1, so it won't affect the constant. So I'll get my 1 over 4 minus 2 over 5 plus 1 over 6. Then if I repeat the process again, replacing every x by 0, the lower limit will just be zeros, so I won't bother much about the lower limit. So the only thing I have to concern myself with are the upper limit, and that means I have to use my calculator to take 1 on 4, that is the first term, minus 2 on 5, the second term, then plus 1 over 6, 1 on 6, that's my last term, that gives me 1 over 16, then I'll multiply by 2 pi, density is not in the calculator, so I'll multiply my answer by 2 pi, that gives me 1 over 30 pi density. So it shows to me that my moment of inertia is 1 on 30 pi density. So guys, that's how simple it is to get our moment of inertia. And finally, there was a last part, which was the D part, which said we should express our answer in the C part in terms of the mass. So when I'm expressing my moment of inertia in terms of the mass, the simple thing you do is that you take this answer for moment of inertia, excluding the density, you divide by your answer for the volume. Why are we dividing by volume? If you go to page 5 of your formula sheet, you will see that there is a relationship saying density multiplied by volume is equal to mass. So if you make density the subject, it will be mass over volume. So that's the reason why we are dividing by the volume. So I will take my answer for moment of inertia, which is pi over 30. I divide by my answer for the volume. My volume was pi over 6, but you see that in my division, I don't include density because I must have replaced density by mass over volume. So if I put mass out here, then it will gives me 1 over 5 m. So it shows to me that my moment of inertia is 1 over 5 m. So I've written my answer for moment of inertia in terms of m. So ladies and gentlemen, that's how we handle this thing. Thank you very much.